Hi class, we are now in chapter 8.5. This is limiting reactant theoretical yield and percent yield. So what a limiting reactant is a substance that's used up first. It limits how much product that can be produced. So for instance, if we look at these hot dog and buns, we can only have as many hot dogs as we have of the least amount of one of the reactants. So in this case, we have only 2 buns but 3 hot dogs. So that means that we can only make or have 2 hot dogs and a hot dog and a bun and 1 hot dog by itself. So in this case, the limiting is the bun, and the excess, whatever's left over that can't be placed into the hot dog and a bun, is called the excess reactant. So this would be the limiting reactant, the one that's used up first, limits the amount of product, and the substance that's left over at the end of the reaction is called the excess. So let's go back to this pancakes. We discussed in another section 1 cup of flour, 2 eggs, half a teaspoon of baking powder, and that produces 5 pancakes. However, now we're going to look into this a little bit more. Suppose we have 3 cups of flour, 10 eggs, 4 teaspoons of baking powder. So we have more than what is called in the original recipe. Now we want to see how much we can make with this extra ingredients. So we set up the 3 cups of flour from the 1 cup ratio of flour to the 5 pancakes, and that gives us 15 pancakes. We then do the same with the eggs and the teaspoons. So we come out with the 3 cups of flour, we can have 15 pancakes. With the 10 eggs, we have 25 pancakes. And with the 4 teaspoons of baking powder, we can make 40. So now these are not matching the amounts here. So something's going to have to change here. So what it is that we can only make the smallest amount. Why can we only make the smallest amount? Because we'll run out of flour before we get past the 15 pancakes. Once we get to 15 pancakes, everything else will not have flour in it. So we won't be able to continue on making the pancakes. That is the substance that's used up first, and it limits how much product it can form. So the other products are excess and reactant because we can't use them anymore. Once we get to 15 pancakes, the smallest amount, we're done. So in this case, this is the limiting reactant, and it's also what we call a theoretical yield. That is the most that we can make without, if you were to go on paper, when we calculate this on paper, without considering errors or any problems, and that we deliver the correct amounts every single time, we can make 15 pancakes. That's what a theoretical yield is. The max amount that can be produced without any errors whatsoever. So suppose we cook these pancakes, and out of the 15, we burn 3 of them, and 1 falls on the floor. So we no longer have 15 pancakes, we have only 11. The 11 is called our actual yield. That is the amount that was actually produced, in this case, in a kitchen, but we will call, when we revert to chemistry, in a lab. That's by the chemical reaction. So we wanted 15, we got 11. That's our actual yield from the theoretical yield. And that's where the percent yield comes in. We have our percent yield is the theoretical, and the actual is over the theoretical. So in this case, we have 11 pancakes over 15 pancakes. We times it by 100 because percent yield is out of 100, so it's always only out of 100, and that gives us 73%. So our percent yield, that means how much we produced out of this recipe, was 73%. Since 4 of the pancakes were ruined, that accounts for the 73% because this is out of 15. Okay, so the actual yield of a chemical reaction must be determined experimentally and depends on the reaction conditions. So this is what would be when we're crossing over to chemistry in the lab. What is determined, actually produced in the lab. The actual yield is almost always less than 100. It should be 100 or less, and the reason being is that it's a percent. If you have over 100, when we do this experiments in lab, when we do reactions, they will always ask, if you work in a lab, what is the percent yield of a reaction? And it should always be under 100. If it's over 100, you actually have some impurities or some side reaction that took place. Something's gone wrong because it shouldn't be over 100. Some of the product does not form, so that's why you always expect it to be under 100. You will never always get to the theoretical yield. That is perfect conditions, and nobody ever does that. Human error alone will make sure that doesn't happen. Product is lost in the process of recovery, and that the more steps you have when you're working in a lab, the more chance you have of losing your reaction. So here is a definition of everything that I've just discussed. Let's do some problems to help you understand how to do this. So we're going to start out very simply. We have a problem here that wants to know the limiting reactant and the theoretical yield. Now here's the thing about limiting reactants. They never change. They may seem very confusing, and as chemistry problems get more complicated, they can overwhelm. But you have to remember something about limiting reactants. Limiting reactants will always give you both values to the reactants. You will always, that does not change when you're given these problems. You will always be given both amounts because you have to calculate through both amounts to determine which one is the limiting. So in this case, you're given the amounts, which is exactly what I said. You have 1 mole of Ti and you have 3.2 of Cl2. You're given both amounts. That's a sign. Write it down if it helps you, that when you're dealing with the limiting, you are always given, no matter how complicated the problem, both values to the reactants, because you have to see which one produces the smaller amount of the product. So that's what these boxes below is, that we need to calculate two separate calculations because we have two different reactants. So we need to take the moles of Ti and determine how much product is produced, and do the same with the Cl2 and determine how much product is produced from that value, because the values that you're given you cannot tell just by looking at those numbers. That will never apply. You have to actually physically do the calculations. So if we do the calculations, we see that with those values we end up with 1.8 of TiCl4 and we end up with 1.6 of TiCl4, and that is with that's why I say it's deceiving, because we started out with more mole of chloride than we did of the Ti, and it still ends up being the limiting reactant. So you physically have to calculate these out. So limiting reactant, you are given always both values of the reactants. You have to calculate both out to the product of which one's being asked, and the smaller amount is the limiting reactant. It will never get to the 1.8 amount because you'll run out of chloride before you can get to this amount. Same with the pancakes. Okay, so let's do some problems. If we have 3 moles of CO and 5 moles of hydrogen, these are the initial reactants. How many moles of methanol can be produced, and what is the limiting reactant? So this is, again, you're given both amounts of reactants. This is a limiting reactant. It won't always tell you that. So you have to look for the shortcuts to help you understand this. So here's the problem. We always need the balanced equation because we need to know the ratios. So we're given the amounts. We know that we need to get to moles of our product, and we need to use some factors in order to determine that. So here's the stepping stones. We calculate separately based on the values that were given and determine the product separately for each of these. And you're given equalities. So 1 mole CO equals 1 mole of CH4O. And then we have 2 moles to 1 mole. And then we can set up our conversion factors that will let us set this up. Okay, so we set up the problem. And you can see here that we start with 3 moles of CO. And on the bottom one, we start with 5 moles of hydrogen. And we go through, and it's even showing you the sig figs. Sig figs from this point on, anytime you do calculations, sig figs are going to follow the rules. You're never going to be able to just ignore them. In fact, because we're online, you're going to need to make sure you understand how to put sig figs in the correct, or it's probably going to mark you wrong. So in this case, we have 3 sig figs. This is exact. We don't need to worry about the mole ratios. And then 3 sig figs at the end. Here we have 3 sig figs. Mole ratios are exact. And then we end up with 2.5 moles. So the smaller amount is always the one that will be produced. The larger amount will never get to completion. So hydrogen is the limiting reactant here. Okay, so the quantities of reactants can be given also in grams. So right now we're looking at moles, but we can also do this in grams. We need to convert the grams to moles using the molar mass conversion. Then we do the mole to mole factors to convert to moles from reactants to product. And then we do the molar mass to convert the moles of product to grams. So then we can determine which one's the limiting. So let's do a problem. We have, this problem is asking for CO, how many grams of CO are formed from 70 grams of CiO2 and 50 grams of C. So we have our reaction there. We're going to plug this in. So I plug these, what I do is I write a balanced reaction out and I write the amounts out underneath so I can see what I'm working with. So in this case, we need to determine again the limiting reactants, but this time we're working in grams. So we're going to need to get these out of grams. Even though we start with grams, we don't work with grams. We work with moles. That is how we manage to jump from conversion to conversion. So we can never leave this in grams. And now we're going to set this up. So we're going to do stepping stones again. We have grams of Si2, the molar mass, because we need to get to the moles. Then we can do the mole to mole ratio, get to the moles of CO, which is what's being asked of this problem, and then the molar mass, and it'll get us to grams. Same thing with the hydrogen. We're going to go through the same way. Here are our equalities and conversion units. So we have 1 mole of SiO2 or silicon dioxide, which is equal to the molar mass. And then we have 1 mole of C and its molar mass. Then we have our conversion for this. I'm sorry. And then we have 1 mole. So this is pretty much giving you all the conversions and equalities you need so that we can do this problem. Okay, so let's set this up. We have our 70 grams. We get that out of grams into the molar mass. We set up the ratio. And then from there we have our molar mass of carbon monoxide. And it gives us a product of 65.3 grams of carbon monoxide. Now we do the same for the bottom. We have 50 grams of carbon, set it up with the molar mass, get the molar ratio, get the molar mass of CO, and it gives us 77.7 grams. And you can see where the sig figs all fit into this. And the smaller amount is the limiting reactant. It's not going to go to completion with the higher amount. So in this case, silicon dioxide is the limiting reactant in this problem. So now we're going to expand on that and go into actual yield and theoretical yield. So when a reaction doesn't go to completion, I already discussed this, but just to review, some of the reactant or product is lost and the amount it produced is less. So theoretical is the max amount that is calculated using the balanced equation. It should always be larger than the actual because this is on paper. Think of theory. This is a theoretical, what you calculated on paper in perfect conditions with no errors whatsoever. It should always be larger than the actual. And the actual is what was physically done, what was completed in a lab. And the percent yield is a ratio of those to determine how much was produced from what was shown as the theoretical. So the difference from the theoretical. All right, so let's do a problem. On the space shuttle, lithium hydroxide was used to absorb exhaled CO2 from breathing air to form, I forgot what this is called, LiHCO3, sorry. I can't remember what it's called. Lithium hydrogen carbonate or lithium bicarbonate. What is the percent yield of the reaction if 50 grams of lithium hydroxide to give 72.8 grams of our product? Okay, so this is asking for a percent yield on here. So you have to learn how to pull out the information. Most cases, you're going to have to go from beginning to completion, which means that you'll be given a limiting reactant problem. You'll have to go through the whole problem, and then you'll be given a certain amount at the end, and you'll have to give a percent yield. So you'll go through the entire step. For now, we're just breaking it down into steps to help you understand. So what is the percent yield? Let's read this problem again. You were given, what is the percent yield of the reaction if 50 grams of lithium hydroxide gives 72.8 grams of lithium bicarbonate? So in this case, the actual yield was 72.8 grams. So we are going to now figure out what the theoretical is. So we're given 50 grams, and we need to get out of grams to moles, and then we do the mole to mole factor, and then we get the moles of our product and the molar mass. We are determining the theoretical. So the actual was given. where we need to know the theoretical. So remember, the theoretical should be larger than the actual, because the theoretical is what's on paper, what's been calculated. All right, so we have our lithium here, and we have our conversions inequality. So I'm just going to skip that step, or that slide, and then set it up. So we have 50 grams of lithium hydroxide. We use the molar mass. We get our mole ratio, and then we use the molar mass of our product, and that produces 142 grams of our product. Now this is on paper without errors what would be calculated through a calculation, not what was actually physically given. And in these cases, the actual is given to you, and you would always have to determine the theoretical. So these problems can be different. You can be given a problem from the very start where you have to go through the limiting. Then they would give you another where you're doing the limiting tells you what the theoretical yield. Then they would give you an actual yield, and then you would have to do the percent yield. So if I'm not making sense to you, there's just a few different ways that these can be given to you is what I'm saying. All right, so we get our 142 grams. That is our theoretical. Then we put that in the bottom because that's what was calculated. What I'm trying to say is if you're given other problems, you'll always be given the actual yield because you're not physically in a lab, so you can't do the actual physical part. The only part you can do is the theoretical. So if you're given a problem, in such as in this case, it gave you the actual. It's telling you what the actual is without telling you that that's what that is. So that's where it gets tricky, where you have to learn how to read a problem. And first before most, understand that limiting, theoretical, and percent yield, they all go together. So if you're dealing with one, most likely you're going to get the other steps too. So that would reinforce that this is the actual. And then we set it up, the actual over the theoretical times 100 and 51.3% yield. So this reaction, based with that mass amount, produced 51.3% out of 100%.